All right. The next thing that we have is vector line integrals, which we just talked about, conceptually what they are. And in this case, we're going to talk about how to compute them. In order to compute them, it's very similar to what we did with scalar line integrals. So we're going to go ahead and assume that you're given some vector field, capital F, and you're given a path C, and you have arrived or been given a parameterization R that traces that curve C. Then what you'd do is you'd replace every x, y, and z in the vector field with whatever r of t tells you x, y, and z are in terms of t. After that, you still want to calculate the derivative of r prime, but instead of first finding the magnitude and multiplying it, we're going to go ahead and leave it as a vector and do the dot product. Lastly, since t for our parameterization ranges from a to b, we want to make sure we include that in the bounds, a to b. So much like a scalar line integral, it's the process of doing a composition, in other words, converting everything to t's, and then, in one sense or another, multiplying by r prime. In scalar line integral, we first find a magnitude, then multiply. In this case, we're doing a specific type of vector multiplication, which is the dot product. So example 3, we'll take a closer look at this one. So here we're given a vector field, f equals z comma y squared comma x, and we're given some path and a domain for t. So to do this, we'll integrate. So this will be c, the line integral over c, z y squared x dot dr, which we can begin replacing the everything or converting everything over to t's. So this will become the integral from 0 to 2. Our z will become a t squared. Why does z become t squared? Well, look at our parameterization. The z component is t squared. So this z gets replaced with what z is equal to on our parameterization, which is t squared. Similarly, y gets replaced with e to the t, and y squared is e to the 2t. The x component of our parameterization is t plus 1. And we'll go ahead and dot that with the derivative, which is 1 e to the t 2t dt. We'll go ahead and do our dot product to get t squared plus e to the 3t, plus we'll distribute the 2t to get 2t squared plus 2t dt. Skipping some steps in here, we should end up with this equaling 1/3 times the quantity 35 plus e to the 6th. And that's a very straightforward way how to compute a vector line integral.